Good morning, beautiful physics kids. We're going to be studying now a whole new unit, a unit called electricity. And as in all new units in physics, you will see the world differently at the end of this unit, substantially differently than you see it right now. If you were to walk into, say, Hogwarts and look on Dumbledore's desk, you would expect to see all sorts of magical devices. Well, Hogwarts doesn't exist. Sorry to break your hearts, it doesn't. But are there things that look a whole lot like magical devices? Well, if you would like to see such things, you'd want to go to a physicist's desk. You might see stuff like this. Now, some might call this, hey, just a piece of junk. It's an old motor that you took apart. Ah, yes, but this, the armature winding, this produces something quite akin to a magical force. As a matter of fact, because we don't really understand it, it is a magical force. The electromotive force. Forces produced by moving electrons. The electromagnetic force would be another way to talk about it. These forces move physical objects, almost like magic, a lot like magic. So let's get into electricity. Now, when we first start studying electricity, you might start thinking we're going to be talking about circuits and wires and all of that stuff, and you would be correct, of course, but that's not what we're really starting with. What we're really going to teach you is how come this stapler doesn't just pass through my hand when I slap my hand with it? What's stopping it? When I smack the table, what's stopping me? Now, before this, you might say, well, the table's stopping you. You can't go through a table. Let's look at what matter really is made of, shall we? We know that an atom is that. This is the electron shell. The electron is incredibly tiny, as tiny as you could get. It's a point particle, no volume. The proton and neutron, depending on which atom you have, is way down in the middle. And what's everything else? Well, it's all empty space. So there's really nothing there. If I had a marble here, the electrons would be, what, nearly a mile away? It's all empty space. If that marble was the proton, the electron's a mile away. That represents the atom? Give me a break. There's nothing here. So how on earth can my hand stop when it hits the table? It's not hitting anything. Blows your mind. Are you hearing that ringing again? It blows your mind. What's stopping my hand when it hits the table is electrical force, nothing else. So there's your first mind-blowing thing. The reason you can walk across the floor and you don't fall right into the earth, the reason the earth doesn't fall into itself, it's all supported by electrical forces. Now, what do we mean by that? What kind of electrical forces? Well, you probably learned a long, long time ago, how do two electrons feel about each other? How do they feel about each other? They are repelled by each other. So if you have them here, each is experiencing a force pushing away from each other. And furthermore, if you get them closer, they repel much stronger. Why? Remember that inverse square law? That if you have energy at a distance, gravity at a distance, if you get twice as far from a gravity field, the gravity pulling on you drops off not by half, but by 1/4. The inverse square law certainly applies right here. So atomic structure makes all of this possible. Some atoms are huge atoms, and in the outermost shell, they share their electrons very freely with all the other similar atoms. These are called metal atoms. So they share electrons. They're conductive. They would be conductors. Other atoms keep their electrons to themselves and aren't sharing with anybody. Those would be insulators. Then we have a whole other class of materials, a few of them, called semiconductors. Sometimes conduct, sometimes insulate. And those semiconductors are what we've built our entire computer industry on. These are amazing things that we can use and tweak so we can essentially turn them on and off so they can store and process information in our modern computing world. So, if we have an object like a sphere, start off with thinking about spheres. If I have an object like a sphere and I have put electrons all over it, they repel each other. They would like to push apart from each other, okay? If I have another sphere here, and I also have electrons all over that, and I use these two spheres as sort of demonstration thing. Now, why spheres? Well, electrons will stay on spheres. If you have a point, electrons will run up to that point and stream off into space. But spheres can hold onto their electrons very well. Well, if we're thinking about this, it starts acting a little bit like gravity, doesn't it? In other words, if I double the amount of electrons on this sphere, how much harder will it repel that sphere? Twice as much. Excellent. What if I double also the number of electrons on this sphere? So I've doubled the electrons on both spheres. Well, how much harder will they repel each other? Well, 4 times as hard. Does this start sounding like the gravitational formula? It should. So what we realize right away is we get this wonderful formula. What force, F sub E, the force electrical, is going to be proportional to, and we have a new unit here, Q for charge. Q on the first sphere times the charge on the second sphere. Nice relationship. Now, if we look at this, again, we have a sphere here, sphere here. What if I move this sphere to this distance away? I've doubled the distance, d times 2. What do you suppose happens? What law governs this? Our good friend, the inverse square law. So, the formula, F sub E, is proportional to charge on one sphere multiplied by the charge on the other sphere divided by the distance squared between them. So it's still a proportionality. We hate proportionalities. If we're going to get rid of this proportionality, we need to do some things. First of all, we need to quantify the electrons. Understand, a single electron is one very tiny thing, doesn't have much charge at all. It's really, in our macroscopic universe, it's really inconvenient to talk about a single electron. So rather, we group the electrons into large herds of electrons. How many electrons are in the standard herd of electrons? Sit down. One herd of electrons is called 1 coulomb. And 1 coulomb is 6.25 times 10 to the 18th electrons. There's a lot of electrons there, right? So we group them and we call that 1 coulomb. So up here, that charge we'd be measuring in coulombs, okay? You already know distance is still going to be measured in meters, but now we at least can talk about the numbers of electrons there. So that's the first big understanding, is how many electrons in a coulomb, but at the same time, we also want to know the charge on a single electron in terms of coulombs. Goodness gracious, how would we do that? Well, if it's 6.25 times 10 to the 18th electrons in a coulomb, and we want to know how many coulombs per electron, just take 6.25 times 10 to the 18th and hit your reciprocal key, your 1 over x key, and you will get that one electron has a charge on it of 1.6 times 10 to the minus 19th coulombs. 10 to the minus 19th coulombs. So that is the charge on a single electron. All right, so we're moving along with this. We can now get back to this formula and we can fix it. We need to put a constant of proportionality here. And the constant is little k. And its number might surprise you. A coulomb of electrons next to another coulomb of electrons, separated by a distance of 1 meter. The force either attracting or repelling, you'll understand, if you're lacking a coulomb of electrons, you're positively charged. And if you have an extra coulomb of electrons, you're negatively charged. So it might be attractive or repulsive, but in any case, that force, K equals 9.0. In your reference tables, it says 8.99. Oh, you can round to 9.0. 9.0 times 10 to the 9th Newton meters squared per coulomb squared. 9 with 9 zeros after it. That would be 9 billion newtons worth of force between 2 coulombs. One of the problems in physics today is we don't understand why gravity is so incredibly weak. Now, even though that's what's governing the universe, making things do all the things we see galactically in solar systems, everything is orbiting each other using the force of gravity. But we still don't understand how gravity can be so weak when electricity and some of the other forces are so incredibly strong. It's a problem in physics, and someday we'll be working it out. But suffice to say, it produces an amazingly strong force between these objects. All right? So this would be Coulomb's law, and it's a good starting place. We want to be able to measure tiny electrical forces so we can play with them. And one of the devices we use to do that is this device here. This is called an electroscope. And in an electroscope, you have these two pieces of aluminum foil hanging next to each other, hanging on a stem connected to this ball. Now, if I charge this up, whether they're positively or negatively charged, the aluminum foil strips will be separated from each other. So this is how I can charge them. What an odd thing. This is bear fur. Go figure. I didn't get it. It was in the box. Bear fur. And this is a rubber rod. Now, why are we using these? Well, it turns out fur doesn't hold its electrons all that tightly. The rubber grabs the electrons more tightly. So if I rub them next to each other, this rod is charged negatively. And if I hold this next to the electroscope, I can place some electrons on the electroscope. And you see the leaves push apart from each other, showing that there's a charge on this electroscope. So I want to do some diagrams here and give you the idea of what an electroscope can be used for in terms of the charge. So let me grab this and erase stuff here. So here's the electroscope, the stem, and the leaves. And I have the leaves a little separated. This would be there hanging straight down. So I have charged this electroscope negatively, and there's negative charge then that has gone down to the leaves and has pushed them apart. So what would happen in this case if I held, say, another rod next to, but not touching it? When I touched it, I charged it by conduction. In this case, I'm inducing a charge. Now, induction means I'm not actually touching it. I'm just pushing charge around inside it. So if this rod was negatively charged, what would happen to the electrons here? Well, they'd repel each other, wouldn't they? Where would they go? Well, they'd go down into the leaves. There'd be more electrons in the leaves. And what would the leaves do? Good, the leaves would push apart more. So a negatively charged electroscope, if I held a negatively charged rod next to it, the leaves would push apart from each other. Well, let's take the same situation. Negatively charged electroscope. But now I have positive charges here. Well, what are positive charges going to do? Well, they would attract the electrons. Now notice we're always talking about the movement of an electron in a solid. Are protons going to move in a solid? Think about that. Would protons move in a solid? Well, protons are the central part of the atom. The atoms are not going to be moving around in a solid, but the electrons, at least if it's in a conductive solid, find no problem moving around in that solid. So it's always, in a solid anyway, it's always the electrons that are moving. So in this case, positive, what's going to happen? it's going to attract the electrons. So electrons are going to move out of the leaves. So there's going to be less electrons in the leaves, and the electrons are going to move up here to be chummy with the positive charges. So the leaves, in that case, would go in. So the electroscope you can play with in various ways to determine electrical charge and how these things work. So that's how you'd play with an electroscope and how you'd use it to determine some charge. It's also, how come your hair gets staticky in the morning when you brush it with a comb? The comb likes electrons, your hair gives up electrons. You brush it a few times, especially if it's a dry day, your hair's going to get staticky. Well, why a dry day? Look at what a water molecule looks like. It's, if you know chemistry, it's a polar molecule. One side's positive, one side's negative. Which means if you have a lot of water molecules in the air, they're going to assist in transferring electrons from one thing to another, so your hair doesn't get very staticky. But if you don't have any water molecules in the air, is there anything that'll help transfer the electrons? Absolutely not. And you'll get quite the static charge. All right, so hey, we're moving along nicely here. I think there's only one more thing I want to accomplish today, and that is to show how we would draw an electric field. So let's take a look at how we're going to be drawing an electric field, shall we? So, let's start out by drawing a gravitational field. If I were to hang something, this is pointing straight down because I'm hanging it. Does gravity work the other way? No! So if I draw a gravitational field around Earth, all I have to do is hang something down and see which way it points. And you know it points down. If I'm here, the gravity field points down. If I'm here, the gravity field points that way, this way. In every case, the gravity field of the Earth is very easy to determine. Why? It only points one way. Do we have that convenience with an electrical field? Well, let's look. If I have that sphere again, and I have it negatively charged, with a lot of electrons on it, which way is the electric field? I hope you realize the answer depends. If I have a negative particle here, well, the electric field would be going that way if I use that to measure it. If I have a positive particle here, the electric field will go that way, if that's what I use to measure it. So it could go either way. Well, that's really inconvenient if you're a physicist studying electricity. You can't have it go either way. Papers that one person does will confuse somebody else, will seem completely wrong to somebody else. So we need to choose before we can even start going. We have to decide, is our test particle, is it going to be negative or is it going to be positive? How do you feel today? I don't know, kind of perky? Yeah, okay, let's choose a positive test charge, because that's what the physicists chose. So anytime you're going to measure an electrical field, you use a positive test charge. If you want to use a negative test charge, well, then you will be wrong, always. So don't do that. Use a positive test charge. Am I sure? I'm positive. I hope you remember that. Anyway, so we use a positive test charge. Don't even worry about what the lines are supposed to look like. Just put a positive charge there. I put a positive charge here. What happened? Oh, look at that. Pulled in. Put a positive test charge. What? Oh, look at that. So in each case, it is like that. That's the electric field around a negative sphere. Okay? Going to do a couple other electrical fields for you. How about if I have two spheres, and I'm going to tell you here is what the electrical field looks like between these two spheres. Your job is to tell me what each sphere is charged as. But don't even worry about it. What do? Did you say put a positive test charge there? Let's do that. So if I have a positive test charge here, positive test charge, oh, and it's attracted to that, what must be the charge here? Negative. If it's repulsed by this, what must be the charge here? Positive. Are we sure? Let's just work a few more. How about a positive test charge here? Well, it's repelled. That's the way it's going. How about a positive test charge here? It's attracted. That's the way it's going. that's the way they'd be. Right? This is pretty easy, as long as you use a, did you say positive test charge? You're paying attention. One more that turns out to be pretty important in the history of understanding this stuff. Check it out. If I have two metal plates absolutely parallel with each other, oh, why don't I let you try to figure this out? I hope I didn't ruin the suspense. If the electric field between these two plates is in this direction, what's the charge on the top? What's the charge on the bottom? I don't know. Put a positive test charge in. There's nothing to memorize here other than a positive test charge. So if I use a positive test charge right where that electrical field is, what must be the charge on top? Well, it must be positive because it's repelling it, right? And it must be negative across the bottom. Now, why spend a little bit of time on this? Two metal plates parallel to each other with opposite charges. The electric field between them is perfectly uniform. That means that at position A, position B, position C, there is no variation whatsoever in the strength of the electric field. Now, as we move into electrons and you see the history of trying to figure out the actual charge per electron, that's a really hard thing to determine. This is the device that was used, so we'll need this a little bit. The only place this is not uniform is on the outside of the plates, where you'd have a bend like that. But in between the plates, it's perfectly uniform. So that's how we use electric fields to determine this stuff. All right? I'm going to show you some demos later and such like that, but thanks for watching. Beginnings of electricity. Do you see the world a little bit differently? When you walk on the floor, can you even touch the floor? You have electrons on the bottom of the atoms of your shoes. The floor has electrons on its upper surface, on all its surfaces, but on its upper surface, it's electrons. Can your electrons touch those electrons? No, they can't. The closer they get, the more the repulsive force. The inverse square law guarantees that. So you float above the floor. You can't actually touch anything. Now this is at a sub microscopic level, so it certainly feels like you're in contact with things. But that's not really the way the world works. You're actually floating above the floor. When you're sitting in your chair watching this, you're floating above your chair. I didn't make this stuff up. Pretty crazy, isn't it? See you next time. Thanks.